So just about a minute. Thank you to all who are joining us in our Zoom meeting. And we'll just get started at 11. All right, well, welcome everybody for our 11 a.m. Tuesday class with Michael Simoniello. In a moment, I will turn it over to him so that he can talk about diving deeper into climate change, or in fact, just talk about climate change. My name is Drew Bush, and I'm the Director of Programs at the Fairbanks Museum and Planetarium. And I just want to welcome everybody joining us on Zoom or on our YouTube live stream, or who may be viewing this again later on Kingdom Access Television or your local cable affiliate. Of course, you can find all of our online programs at fairbanksmuseum.org. I just also want to remind folks who are in Zoom that you can interact in our presentation today. There's a Q&A button down at the bottom that it looks like somebody has already found. You can ask your questions there. We'll either answer them live in our session, or we will type you a written response. And you can also chat with us over in our chat box to the right of that button in Zoom. For those of you on YouTube live stream, or maybe seeing this on cable access, feel free to send your questions either before a class or during a class to dbush@fairbanksmuseum.org. We're happy to answer them whenever we can, even if it's for our next class. And just remember that we are recording this video, so if you choose to interact, be aware that that is a part of our class recording often. So without further ado, I will now turn things over to Michael Simoniello so you guys can learn some about climate change.
Okay, thank you very much, Drew. Welcome everybody to diving deep into climate change. So in this class today, we're going to discuss really the actual physical science that's driving climate change. So the Earth's processes and the human causes that all go into the Earth's changing climate. So this is a very, very common, very popular point of discussion, topic of discussion in today's world, but the real science and data behind it is often not as well known as it should be. So this class will hopefully give you a really good footing to think about and discuss climate change. Before we get started here, I do want to ask, please be forthcoming with your questions. Some of these topics will be a little tricky. I want to make sure that everybody, has a really good understanding. If you have any kind of question, please feel free to ask. And then also, I'd like to invite Drew to also ask questions and correct me and help out. Drew, of course, is an actual expert in climate change. He's done a lot of postdoctoral work on the subject, so he's an excellent resource for me and for you. So that said, we're going to begin this discussion here really by introducing you, maybe, but hopefully refamiliarizing you with one of really the world's greatest proponents for climate change activism, right? One of the people in our world who is the most popular voice right now for climate change, and that would be Greta Thunberg, who is a young person, much younger than me, but who has really taken the international stage here in discussing climate change. So, oh, hold on, I have to get my link. Here it is. Give me one moment. It sometimes doesn't work super well. Can you see my screen, Drew? Okay.
We're seeing your slide.
Okay, yeah, I'm trying to load the video from the slide. I only tried this on my other computer where it worked much more smoothly than this. Either way, this is a speech given by Greta Thunberg to the United Nations. Really, it's a call for action to change, not only the laws of the nations of the world, but also individual people's habits and activities in order to affect climate change in a positive way. Maybe this won't load for me here. I apologize. Hold on. Oh gosh. Oh, there we go. Are you seeing the YouTube page, Drew?
Not yet. I think we're still looking at your slides, and I can grab the video too. I'm just pulling it up.
Something is not working here.
Okay, well,
I'm sorry.
Let me grab it for you. I got it right here. I almost got it.
Yeah,
right.
I'm sorry. Okay. Thank you.
Just need to find the link.
Here, let me stop my sharing. Well, this is unfortunate. I think that trying to load the video and having Zoom operating at the same time is really not working.
Yeah. That's okay. It should be okay for me. I'm plugged into the Ethernet over here.
Yes.
Sorry, everybody, while we encounter a few technical difficulties, but we're right. Just about there. I'm just getting the right video. Here we go, guys. And apologies for our slow little bit of technical difficulties, but does anybody, Michael, do you want to say anything a little bit more about who Greta is before we play this?
Yeah, so Greta is a young woman from Sweden, right? Or Norway, I always forget. Sweden, right? She's a young girl from Sweden. She's only about 14 years old, so she's in terms of American school, she would be going into her first year of high school now, and she's become relatively famous across the world for organizing student strikes for climate referendums. So in order to get the attention of the Swedish government and governments across the world, trying to force them to change their policies in terms of how they use fossil fuels, how they develop land, all of these things that we'll learn about in a couple of minutes have a deep impact on the environment. And if we continue to burn fossil fuel or use our land inappropriately, we're only going to see climate change get worse and become more of an international crisis. So Greta is a very youthful and forceful voice, trying to enact this type of change. So yeah, you'll see that in this video here. We'll only play a minute or two of it. So Drew,
okay.
you can start it, and I'll try to let you know about where I am.
Raise your hand. I'll stop it wherever you want me to.
Okay. Watching you. This is all wrong. I shouldn't be up here. I should be back in school on the other side of the ocean. Yet you all come to us young people for hope. How dare you? You have stolen my dreams and my childhood with your empty words, and yet I'm one of the lucky ones. People are suffering, people are dying, entire ecosystems are collapsing. We are in the beginning of a mass extinction, and all you can talk about is money and fairy tales of eternal economic growth. How dare you?
Okay, Drew, you can stop it here if you like.
All right, so I'll turn off my screen and take it.
Okay. So you can tell just from that short snippet that climate change and the crisis of global warming is something that really inspires passion in a lot of particularly young people. And you might be thinking, if this is such a large crisis, a serious international issue, why aren't we more informed about what's going on? Why isn't the science readily available to us? Why aren't our governments doing anything about it right now in the moment? And so this class is, intended to kind of make a lot of this science clearer to you. So we're going to begin with really the Earth forces that drive climate change over a long period of time. Climate change, the warming and cooling of planet Earth, isn't something that's brand new. It's not a novel process. Climate change has been happening on our Earth for the past 200 million years more, since the Earth first began to form. And in fact, climate change has always occurred in cycles, mathematically predictable cycles. We'll talk about those cycles in a moment. But it's important to know that these cycles that the Earth goes through, of course, you've heard of ice ages, right? The last ice age was about 15,000 years ago, is the last glacial maximum. So that would be at a time when glaciers covered Vermont. But there have been many ice ages over the course of the Earth's history. And it's important to know that humans have only been around for less than 1 million years on the Earth here, whereas the Earth is many hundreds of years old. So while these cycles have been happening on the Earth for as long as it's been around, this is the very first time that humans have been experiencing the changing climate of the Earth. And like any animal, humans have to either adapt to these changes or go extinct, right? 99% of every species that has ever existed on the Earth has gone extinct. And humans are no exception to rules like that. So we have a question, Drew?
Yeah, so we have a question on topic for what you're talking about. Does climate change mess everything up? So that's a good question, right? Depends on your perspective.
Right. Well, yeah, it does depend on your perspective. And most of us, being humans, we have a very human perspective, right? And in terms of human life, yes, climate change will certainly begin to mess everything up for us. As I've been saying, humans have only been on this Earth for less than 1 million years, but we are, what's the best way to say this? We have been used to living in very specific conditions here on the Earth. And as those conditions change, as the Earth heats up dramatically, as sea levels rise, we could see a lot of our coastal cities go underwater. Just as the Earth warms, it's going to cause a lot of problems for humans, and also the natural world itself. You could think about it in some ways as we're kind of poisoning the atmosphere and the land of our Earth by really messing with the Earth's natural cycles of climate change. Really, what we're going to be discussing in today's class is the fact that while the Earth goes through natural cycles of climate change, humans have been able to mess with those cycles so much that the way that the Earth is now changing doesn't reflect those cycles. Now, those cycles happen over such a long period of time that, eventually they will probably even out. But for the short term, and of course, by short term, I mean, the next couple hundred years, in terms of the life of the planet, that is the short term. But over the next couple hundred years, we might unfortunately affect the Earth so much that we make it impossible for us to continue living here. And certainly it will be impossible for us to continue living on the Earth in the way that we have for the past couple hundred years. So let's just begin with a couple slides here. We'll take a question and then we'll get right into the science and the data. So yes, Drew?
Oh, actually, I'll just type an answer to this question. We're good.
Okay. So back to my slides here. Okay. So we're going to begin by talking about the greenhouse effect. You've all probably heard of the greenhouse effect and greenhouse gases. And in simple terms, the greenhouse effect basically means that the Earth's atmosphere, all of the air that's trapped around the Earth in a relatively thin layer of air above the ground, really acts exactly like how a greenhouse acts. And now you should all know the purpose of a greenhouse is to trap solar radiation, light from the sun, in order to basically warm the ground or the soil inside of the greenhouse so that you can grow plants out of season, right? You can see here in this image, the atmosphere works like a greenhouse around the Earth. Well, the greenhouse gases in the atmosphere work like a greenhouse around the Earth in that they can trap in solar radiation in the form of heat. And this is what is causing our Earth right now to warm. The greenhouse effect of our atmosphere is starting to go out of control in an unnatural way. Because of humans burning fossil fuels and by changing the land, by clearing land, by cutting down trees, by burning land, we are putting too much greenhouse gas into our atmosphere. And this is basically like thickening the greenhouse around the Earth, where it's trapping in more heat in the Earth's atmosphere and is warming up the Earth. And this is not part of the natural cycles of the Earth's heating and cooling. Right now, based on the orbital cycles that the Earth goes through that we'll talk about in a little bit, the Earth's climate should be gradually cooling. And in fact, the upper atmosphere, the highest parts of our atmosphere are cooling, because that would be the current natural process. But because of humans, we are building up this greenhouse effect across our Earth. And unfortunately, the lower parts of the atmosphere, of course, where human beings are, is getting warmer, and it's getting warmer quickly. In order to make sense of how this greenhouse effect works, both in the atmosphere and in any greenhouse that you might find on a farm or in your backyard, you have to understand a little bit about the electromagnetic spectrum. Now, this is a scary sounding topic. During my energy class, if any of you tuned in for that, we learned a little bit about the electromagnetic spectrum. The place where we encounter the electromagnetic spectrum most obviously and most often in our everyday life is in light, simply. Light is a form of electromagnetic wave, whether it's being emitted from the sun or whether it's being emitted from a lamp in your house. It is a wave that carries electromagnetic energy, and our eyeballs, our bodies experience it as light. But now we can only see a very small section of this very large electromagnetic spectrum. And that section that we can see, we call visible light, of course. The forms of visible light you can see very easily every time you see a rainbow outside. When water molecules in the air work like a prism and they split the light that comes out of the sun, we can see it in the colors of the rainbow. Each one of those colors represents a different wavelength in this electromagnetic spectrum. On this graph that you can see here, the left side of the spectrum, these are we call them long waves, which means that they're very tall and there's a lot of distance between the peaks and troughs of the wave. All the way on this side, we have things like radio waves, which of course we can't see because they're not part of the visible spectrum, but they're all around us. Radio waves are what powers our phone calls. It's what we pick up with our radios. And these radio waves can actually be as tall as buildings. They're massive and they can move through solid objects. And of course, we're a little bit familiar with how radios work. So that's an easy one to think about. We know that there are these invisible radio waves that are moving through our atmosphere all the time. But what we normally don't think about is that the light that comes out of our lamps or out of the sun is the exact same type of thing as those radio waves, but just at a very different wavelength and frequency. So now, if you see those two red arrows on my graph here, those bracket out the visible spectrum of light. So all the colors of the rainbow, the light that we see that comes from the sun, which is all of those colors put together. That's why it looks white or kind of yellow. And directly on either side of that bracket, you have infrared light and ultraviolet light. These are two types of electromagnetic waves, two types of light, you could think about it, that are not normally visible to us. They are emitted from the sun, and they interact with our atmosphere in a very specific and interesting way. Now, the sun emits a lot of ultraviolet light, and ultraviolet light is the type of light that gives us sunburns, essentially. You can see that ultraviolet spectrum, that purple block in our spectrum, is in between visible light and X-rays. And we all know that X-rays are quite dangerous to us, right? They're very small, high-frequency waves that can pass through our bodies and actually destroy or mutilate, really, the cells in our bodies. Ultraviolet light really does a similar thing when it burns the skin on your body. These are very high energy waves that can damage your skin cells. As an example of ultraviolet light, I have right here a 30-watt ultraviolet lamp. Now, it might be kind of difficult for you to see this through the camera here, but this is it's a purple light. Let's see if you can see that shining on me here. If you've ever seen what we call a black light or something like that, these are ultraviolet lights. This type of light is purple in hue, and it doesn't necessarily seem very bright, but it is quite dangerous. If I looked into this lamp for even just 30 seconds, I could really seriously damage my eyeballs, even though it doesn't seem very bright. This ultraviolet light is beaming out of the sun and passing through our atmosphere. Some of it gets blocked as it passes through our atmosphere, but some of it also passes straight through and hits the earth, whether it hits the oceans or whether it hits dry land. The effect of this light, as well as the visible light that comes out of the sun, is that it will heat up. This is high energy light. So this light energy, when it hits the earth, transfers to heat energy, and it heats up the oceans, or it heats up the actual ground of the earth. And then as this light passes through the atmosphere, heating up the ground and heating up the earth, it's actually converted into another type or form of energy, which would be the infrared spectrum, the infrared light or infrared energy on the left side of the spectrum. So do we have a question very quickly before we talk about this? Yes.
Yeah, folks are wondering what causes it to bounce back out versus being absorbed. Are there different things in the atmosphere or on the surface that play one role or the other?
Yes. So as light from the sun passes through all the gas in our atmosphere, a lot of this light gets refracted as this beam of light passes through water molecules, other gas molecules in the atmosphere. It can spread out and refract throughout the atmosphere so that not all of it hits the ground. But also, as a lot of this light hits the ground, it does just hit the ground and bounce back up. You've probably heard of the fact that white objects reflect light, whereas black objects absorb light. So for instance, if you think about the polar ice caps, when this when this ultraviolet light passes through the atmosphere and hits ice or snow, most of that light energy is going to be reflected back up into the atmosphere. But the tricky thing about this is that when it hits the ice and then gets reflected, it isn't reflected as ultraviolet radiation. It gets reflected as infrared radiation. So that purple light that you just saw gets transformed into this type of light here. So if you raise chickens at home, you might be familiar with this type of light. It's often called a chicken lamp. But this is an infrared light. You can see pretty clearly that this is certainly a different type of electromagnetic wave than what we just saw with the ultraviolet light. The ultraviolet light is what we call short wave radiation. Those waves are small and fast moving. These waves are larger and slower moving and also create a lot of heat. If you've ever used a chicken lamp like this, even just holding my hand out in front of the lamp, it's getting quite hot already. Whereas that ultraviolet light, even though it can give you a sunburn, you don't feel any heat coming off. And the important thing about this type of light is that these waves, these longer, larger waves, can't get back out through the atmosphere. The atmosphere makes a kind of shield for this radiation. The ultraviolet shortwave radiation is small enough that it can bore straight through the atmosphere and reflect back out into outer space. But this long wave radiation gets trapped in our atmosphere. And in particular, it gets trapped in greenhouse gases. We'll talk about greenhouse gases in a minute, but for right now, you should just understand that the more greenhouse gas you have in the atmosphere, the more of this type of light, this type of radiation, you're going to trap inside of your greenhouse or inside of your atmosphere. In the case of an actual greenhouse, that's what you want to have happen. You want the greenhouse to trap this radiation and stay warm. But on our Earth, it causes some problems when we do this. So I'm going to skip these for just a second. And here is another example of what I'm saying. So the radiation from the sun, the long wave, or the short wave radiation from the sun comes down and hits the Earth. Some of it gets absorbed in the Earth, causing the ground to warm up. Some of it gets reflected. That reflected energy transforms from ultraviolet light into infrared light. And now that we have greenhouse gas in the atmosphere, a lot of it is getting trapped. And instead of going back out into outer space, it stays in the atmosphere and gradually warms it up. Do we have a question? No? Okay. So in terms of the actual gases that we're talking about here with the greenhouse effect, you should know that most of our atmosphere is made up of only two types of gas, and they are not greenhouse gases. Those two gases are nitrogen and oxygen. Nitrogen makes up about 75% or more of our atmosphere, so it's mostly nitrogen. And then about 20% of that atmosphere is oxygen. Oxygen, of course, is the type of gas that we rely on to respirate, to breathe, right? So that makes 95% of our atmosphere is nitrogen and oxygen, if not more, usually. And then the rest of our atmosphere is made up of a little bit of water vapor, which of course we see all the time. We know that our oceans and lakes and rivers, and even from our bodies and from plants, there's evaporation going on. There's water that's leaving the surface of the earth and rising into the atmosphere where it becomes clouds. So of course we know that there's a little bit of water vapor, but that's only a very small amount, fractions of a percent. And then we also have one that you've certainly heard of, carbon dioxide. So this is our first real greenhouse gas. I suppose water vapor could be a greenhouse gas, but that's not one that humans put an unusual amount of into the atmosphere. But when we're talking about carbon dioxide, naturally there is some carbon dioxide in the atmosphere, but a very, very small amount. Human beings have been pumping carbon dioxide into the atmosphere for the past 200 years, since the Industrial Revolution. We've been doing this by burning fossil fuels. Again, if you saw my energy class, you might recall these. This is a jar of crude oil. So this is, of course, organic matter. So very decayed animal bodies, plant material that has over time underneath the earth over the course of 50 million years, then essentially compressed and rotted down into this organic fuel. And then similarly here I have coal, another type of fossil fuel, this in a solid form that's formed from plant matter that has either burned or broken down over time. So when you burn these two substances, these are organic substances that are very, very high in carbon. That's what helps them to burn so well. But of course, when they do burn, it puts all this carbon dioxide into the atmosphere where it's normally not supposed to be. Think about it this way. All of that oil and coal that we're burning is naturally meant to be trapped underground, right? The earth itself, the actual geology, the rocks of the earth are a massive carbon sink. Most of the carbon either in our earth or in the atmosphere is supposed to be deep underground, but we've been mining it up and burning it and throwing it into the atmosphere. And because of that, we've unbalanced the natural carbon cycles of our earth. And so not only is that warming the earth, but it's also causing problems in Earth's really natural or organic cycles. In terms of some of the other greenhouse gases that we can see, methane is one. In Vermont, you should be familiar with methane from dairy farming, right? Cows, ruminants produce an unusually large amount of methane from their digestion. Humans, of course, also produce a little bit of methane. That signature dairy farm smell is methane is responsible for that smell in a large part. And this gas, as it enters the atmosphere, also traps infrared radiation, heats up, and makes our atmosphere warmer. One source of methane that we don't see here in Vermont, that's a massive human cause, is from rice farming. So we don't farm rice in Vermont, but in the southern parts of the United States and also all throughout Asia, rice is farmed on a massive scale. It's a staple food in many, many parts of the earth, and it's farmed really half submerged in water. These are called rice paddies. And these rice paddies actually produce tons and tons of methane every year. There's there's much more methane in the atmosphere now than there normally is because of these human changes. Things like landfills and just really decaying trash also leaks methane out into the atmosphere. Nitrous oxide is another greenhouse gas that you may have heard about, caused by different human production, factories, vehicles, things like that. Chlorofluorocarbon, I always say this wrong. Chlorofluorocarbons are an interesting one. Chlorofluorocarbons are all pretty much 100% human made. There are no natural chlorofluorocarbons entering the atmosphere. The other term that we use for these, the more familiar term, is aerosols, right? In the past, if you're old enough, like my age, to remember this kind of thing, aerosols were common in the news years ago, maybe 10 years ago, particularly because a lot of these aerosols were getting into the atmosphere, and we learned that it was causing a hole in the ozone layer of our atmosphere. So at the outer layers of our atmosphere, there's a layer of ozone gas that actually blocks out a lot of that UV light, a lot of that purple light that I showed you. The aerosols, as they entered the atmosphere, they actually basically ate a large hole in this ozone layer, and that, of course, was not very good. A whole lot of extrasolar radiation was entering the Earth through that hole, and this is really a climate success story. But as a result of people learning about this hole in the ozone layer through satellites, the countries of the Earth banded together and really made many of the most advanced countries made a group decision to try to limit aerosol production and emission into the atmosphere. So you may use aerosols on a daily basis if you use things like spray paint or hairspray or PAM or something like that. All of those products have aerosol in them. But the large factories that emitted lots of aerosol have mostly stopped. And as a result, we've actually fixed, for the most part, this large hole in the ozone layer. So that is a successful story in the epic of climate change. The last type of greenhouse gas that we're going to think about actually is ozone itself. So I just mentioned that ozone, when it's at the edge of the atmosphere, when it's at the very top of our atmosphere, is a good thing. Ozone does belong there, and it helps shield the Earth from extra UV radiation. But ozone is also created by humans in factories and from our cars. And when we burn fossil fuels and release that ozone, it's being released very close to the surface of the Earth, where that ozone doesn't belong. And when ozone is down here by the surface, it does trap a lot of heat, and it actually causes problems. So ozone, when it is close to the surface of the Earth, is a greenhouse gas and is a bad thing. But ozone, where it belongs in the top of the atmosphere, is a good thing. It protects the Earth from radiation. So Drew, did you have a question?
No, actually, I just wanted to clarify too, the ozone hole is pretty separate from climate change as an issue. It actually predates it, you could say, although there's research, of course. There are some scientists who are investigating the relationship between the hole and climate change now, but that connection is still something that I think is, researched and not necessarily confirmed if there is a cause-effect relationship there. But it is a really, really nice story about, how the world can come together to solve an environmental issue that involves atmosphere.
So why were people concerned about the hole in the ozone layer in the first place if it wasn't necessarily a climate change problem?
So it's a separate issue. Ozone at the top of our atmosphere, as you've been talking about this class, blocks ultraviolet radiation, which can cause skin cancer in people. So it actually had a very negative health impact on human health.
Right.
If
So
we
it's
don't,
a human focused issue rather than a
yeah, yeah, and
global
at
health issue.
the top of the atmosphere, it's actually that O3, as you're pointing out, that really forms naturally. So it was only because we had these CFCs that were making their way up into the stratosphere that we had a hole in the ozone. It's
Right.
completely human caused. Also, I would point out a lot simpler of a problem to tackle.
Yes. Yeah. Right.
Because we could simply, regulate these particular compounds that industries or other places used. And, in particular, there was even an alternative available to them too. So, it was easy for some industries to be able to.
Yeah. Okay.
Not the kind of issue like climate change that maybe reaches into every aspect of our modern life.
Right. And where there is no simple alternatives, most of this greenhouse effect that we've been talking about, has been caused in the pursuit of energy for humanity, right? We've burned these fossil fuels over time in order to create electricity, to run our cars, to run our businesses, and things like that. But humans are struggling to find alternative ways to create power, right? Here in Vermont, we've actually done a pretty fair job with finding these alternative power creating methods by building wind farms and burning biofuels like wood instead of fossil fuels. But across the earth, we're really struggling to make the change from fossil fuels to renewable energy. That's really one of the key components of all of this. But so now we've been talking about the greenhouse effect and the human impacts on climate change. So that is really the key of what people are talking about today, the way that humans have changed the climate over the past 200 years. But it's important and essential to know that the Earth's climate has been changing constantly for the past hundreds of millions of years that the Earth has been around. And it's important to understand those causes of climate change and why they're different and distinct from the human causes. So this little pie chart here, you can see greenhouse gases is one of those slices. That is the human slice. That is the part of climate change that we are directly affecting. The rest of those slices are the phenomena that naturally affect our climate. And the common element between all of these other four slices is that they have a much longer time scale than the greenhouse gas effect that humans have caused over the past couple hundred years. For instance, when we talk about something like tectonic motion, which is the very slow movement of the continents and their plates, right? That our continents and even our oceans are basically big puzzle pieces of Earth crust that are floating on liquid magma underneath the crust and move very slowly, crash into one another and move apart. Those movements happen over the course of hundreds of millions of years. If you've ever heard of, Pangea, I have a little diagram of this way down here. Talking about plate tectonics. Pangea up on the top left, that was a time 225 million years ago where all of our continents were stitched together in one massive continent. That's actually happened twice in Earth's history, where the continents have smushed together, come apart again, and then smushed together again. So these tectonic plates are always moving, but never in our lifetimes will we really be able to see the results of these movements. So the other Earth processes that affect climate change are that tectonic motion, which is the slowest thing that over millions and millions, hundreds of millions of years causes the Earth's climate change. But also the sun itself actually goes through cycles 11-year cycles of warming and cooling ever so slightly, but even those very, very slight changes in the sun's solar radiation affect the Earth's climate a little bit. And of course, those cycles are totally out of our control, right? We can't control when the sun heats up and cools down. Astronomical variation is what we're about to talk about. And astronomical variation basically means changes in the actual orbit of the Earth around the sun. And the last one is volcanoes. We'll talk about volcanoes also in a little while. But for right now, I would like to show you guys an excellent article from NASA about climate change, and particularly about what we're going to call Milankovitch cycles. These are the orbital cycles of the Earth. And there are 3 different movements, 3 different cycles that you have to keep in mind when you're talking about these Milankovitch cycles. And the way to think about it is that the Earth, of course, rotates around the sun, but the Earth doesn't rotate perfectly, right? The Earth doesn't rotate in a perfect circle around the sun. It rotates in an ellipse, kind of like an oval, and that ellipse stretches. Sometimes it's almost a perfect circle, but sometimes it squishes down a little bit into more of an oval shape. And that cycle, which you can see right here in this graphic, changes between a more circular orbit and a more oval orbit, happen over a course of 100,000 years. So if you can see here, it takes 100,000 years to go from almost a circle to a long oval and back to almost a circle. You've probably already guessed that these changes in the Earth's orbit affect our climate because as that orbital circle stretches out, our Earth will be farther away from the sun at certain times of years than at other points during this cycle. So the Earth will get less solar radiation when it's farther away from the sun, and as a result be slightly cooler, but not dramatically cooler, right? This difference, this blue line of difference that you see here when the oval stretches out all the way, that's a couple million miles of difference. But even that couple millions of miles of difference out in outer space doesn't make a massive difference on our climate. So right now, in terms of the point in this cycle today, if you look at the bold text down here where it says currently Earth's eccentricity is near its most elliptic, which means it's most oval shaped instead of most circle shaped, and is very slowly decreasing in a cycle that spans 100,000 years. So right now, in terms of this cycle, we are at really, you could think about it as the coldest point, right? The point where the Earth's rotation yearly is most distant from the sun. Yes, Drew?
I don't think your slides are advanced. We're still looking at the pie chart. And
oh, are you? Oh, what the heck?
You may want to make it full screen.
Oh gosh, I'm sorry about that. Oh, I see what I've done. You should have interrupted me earlier. Can you see it now? Ah, that must not have made very much sense without the image. Can you see the graphic now?
Yeah, we can see it now, and maybe we can do a little recap.
Yeah, I'm sorry about that. Right. So you can see here that the Earth does orbit the sun roughly in the shape of a circle. But over time, over a course of 100,000 years, every year, that circle will actually stretch out a little bit for 50,000 years. And every year, that circle will get longer and longer and longer, and it'll look more and more like an oval, right? And then after that, after the oval reaches its maximum ovalness, it'll start to shrink down again, and the orbit will look more like a circle, right? And you can see that difference here in the graphic on this blue line here. That blue line is a difference of a couple million miles, right? Right now, if I could pause this graphic, which I can't, today, the orbit of our Earth around the sun is at its most oval shaped, so at the longest period, which means that during the course of a year today, the Earth receives less solar radiation, less light and heat from the sun than it will 50,000 years from now, when the Earth has a more circular orbit. But even this cycle doesn't change the Earth's atmosphere too much. It's really this cycle that is most important for climate change. When we talk about ice ages, this funny little tilt of the Earth here is what causes those ice ages every 40,000 years. So what we call this cycle the Earth's obliquity, right? The Earth rotates. As the Earth orbits the sun, it also itself rotates, it spins, right? And that's what causes our days and nights, right? As the Earth spins, and some of the Earth faces towards the sun and some of it faces away from the sun, making daytime and nighttime, right? The Earth, of course, since it's spinning, it has to spin along an axis like a top. The axis of the Earth's rotation goes straight through the North and South poles, but that axis isn't straight up and down. You could think about it that way. The Earth the Earth rotates tilted on its side like this. And that's what you could see in this graphic here. But even as the Earth rotates tilted like this, every 25,000 years, is that right? No, 40,000 years, right? Just like the Ice Age cycle, of course. Duh. Every 40,000 years, that axis actually tilts a little bit, and it will get closer to straight up and down or farther away from straight up and down. And what this changes is that, for instance, when the Earth's orbit is most straight up and down, actually, I will stop sharing my screen for just a moment here so that I can show you this on my globe. So when the Earth's orbit, when its obliquity is perpendicular to the sun, it orbits like this, right? And if the sun is over here, the light from the sun, the majority of the solar radiation, is going to be focused along the equator, right? And as the Earth continues to rotate like this in this angle to the sun, the area around the equator is going to receive the majority of the sun's solar radiation, and it's going to warm. But the polar regions, the North Pole and the South Pole, are not going to receive that solar radiation. And as a result, it's going to get much colder at the North Pole and at the South Pole, and they're going to form ice sheets up here. And those ice sheets are going to start extending, and they'll extend all the way down as pretty much as close to the equator as they can get. So 15,000 years ago, when the last glaciers, the Laurentide ice sheet, or the Wisconsin ice sheet, some people call it, as that extended down, it extended down through Vermont, down to Long Island Sound, where it stopped, and then started to retreat. The ice sheet began to melt because the Earth's axis wobbled back this way. And so now the sun is still over here, but now the Earth's axis spins kind of pointing this way. And so now the light from the sun is the radiation from the sun, the heat and light from the sun is warming less the equator and more the southern and northern hemispheres here as the Earth rotates and spins, as it orbits the sun and also spins. So that solar radiation is now shining directly onto those glaciers, those ice sheets, and it's starting to melt them. So the Earth will tip like this every 40,000 years, and we'll get ice ages roughly every 40,000 years. Right now, in terms of the Earth's obliquity cycle, like we were just seeing, we're actually approaching another ice age right now. So over the next 20,000 years, the Earth is going to get cooler and cooler. Well, so where we live in Vermont here, the Earth is going to get, the climate is going to become cooler and cooler until eventually those glaciers return from the North Pole region and cover Vermont. So the big issue here is that we know that the Earth should be slowly cooling off right now. We should be approaching a glacial period where the glaciers return. But the evidence that we're seeing from satellites is that the Earth is getting warmer instead of getting cooler. These cycles, these astronomical cycles of the Earth's orbit changing are very well established. We know that they're not going to change in the next couple million years. And we know that it's supposed to be cooling off. So why the heck is the Earth instead getting warmer? And the statistical reason for that, the scientific reason, is because of the increased greenhouse effect, the global warming that human beings are causing. So we're responsible for for upsetting the natural climate cycles of the Earth. And because we're upsetting these climate cycles, the Earth is rapidly changing, very rapidly, unfortunately. As we warm up the Earth, our ice sheets that we have up on the North and South poles are going to start to melt. And these ice sheets, like we were talking about earlier, are very important for reflecting solar radiation. Those large areas of white ice reflect that radiation right back out into space, hopefully. This is called ice albedo, the ability of ice to reflect that light. But as our atmosphere warms, that ice is starting to melt. And as the ice melts, there's less ice to reflect that solar radiation. So the Earth is going to warm up even faster with less ice. We call this a positive feedback loop, right? The more the Earth warms up, the less ice there is. The less ice there is, the faster the Earth is going to warm up. And the whole cycle just speeds up. This is dangerous for a lot of reasons, right? As the ice melts, sea levels begin to rise and the ocean begins to warm up and become less saline. As those ice caps melt, it changes the actual chemical composition of the ocean. We know that our coral reefs are dying out because of pollution and because of changes to ocean chemistry, right? We know that lots of cities across America and across the world that are built on the edge of the ocean are going to be, eventually swallowed up by the ocean if this continues to happen. It creates a really dangerous situation for all of us humans living here on the Earth. It looks like we're unfortunately just about out of time here. I feel bad leaving it off on an unfortunate note like that, but I guess what I would like to say, just before we leave here, is that all of this should seem pretty dire to you now, the science that I've explained. The fact that we truly have upset the natural state of the Earth, the natural conditions of the Earth. And because we've upset the natural conditions of the Earth, it's going to change human life dramatically, and it's going to change the plant and animal life on the Earth dramatically. And even though these changes are going to be scary and they're going to be negative for humans, we have a lot of knowledge about climate change now. People are starting to understand the science very well. People are starting to recognize climate change as a global crisis, right? So we have all this information. We have people who are passionate and interested in reversing negative climate change. And we are also, especially in places like Vermont, starting to come up with really great new ideas to stop climate change, to stop the advance of climate change. Like I was talking about with renewable energy, with much better power grid systems, people changing their lifestyles, right? Using less disposable products, using less products that are dangerous for the environment, composting more, things like that. So while the situation is dangerous, there is a lot of work that even young people, even students, even individual people can do to help reverse this climate change, and we already are taking steps to do so. So there is a positive outlook for all of this, despite all of the kind of the scary truth of it. So thank you guys very much for coming to my class today.
Yeah, and I want to thank everybody as well. We're happy to have you here, whether you're on YouTube or on Zoom, or maybe catching this later on cable access. Just to add to what Michael's saying, definitely a lot of interesting work taking place on climate change. There's two ways people think about solving it, and maybe that's the topic for a future class. But we think about mitigation. So doing things like Michael talked about, like having more renewable energy so that we can limit the amount of greenhouse gases we as humans put into the atmosphere. And adaptation. So how do we get ready for its impacts, things that we know are going to happen, given the amount of climate change we kind of have already locked in. Right. So thank you again, everybody. A big thanks to Michael Simoniello for teaching our class today, and we'll catch you all soon at fairbanksmuseum.org. Thank you. Bye.
Thank you.